Hello everyone, this is Dr. Abdul Pasha, Assistant Professor, Institute of Aeronautical Engineering, Dundigal, Hyderabad. So we are in the course of Power System Operation and Control. So this will be followed with today's topic, Penalty Factor Analysis. We already discussed in the earlier video about some points regarding penalty factor. And the extension of this penalty factor analysis will be followed now. So what is penalty factor? So in the power system network, penalty factor plays a very important role. While defining economic scheduling of the power system network, penalty factor will be defined. So it is the ratio of plant's power generation. Ratio of plant's power generation to the actual power demand of the load after transmission losses has taken place. So we discussed earlier regarding some transmission loss coefficients and what are the reasons the transmission losses are going to be takes place. So it's also the factor used to multiply the incremental cost of power production. So that is used to define for the account of transmission loss coefficient. So coming to penalty factor analysis, in a power system network, this is a way to account for the transmission losses. When calculating the incremental cost of the power production for a given plant, the penalty factor is the ratio of the power generated by the plant to the actual power demand after transmission losses are going to be taken place. So it's also the factor by which the incremental cost of power production is multiplied to account for transmission loss coefficients. So here is the analysis for penalty factor. We already derived the coordination equation as a dfn by dpn plus a lambda dou pl by dou pn, which is equals to lambda means which is a Lagrangian coefficient. Then dfn by dpn is equals to lambda of 1 minus dou pl by dou pn. So how we are obtaining this relation means just you need to take the lambda here and here as common, and this becomes lambda of 1 minus dou pl by dou pl. This we may obtain. Now dfn by dpn as a product of this coefficient, when you write 1 by 1 minus dou pl by dou pl, we can write like this. When you simplify this condition, the same aspect you may obtain like this. So finally dfn by dpn multiplied with ln gives you Lagrange's coefficient lambda. So where ln is called as penalty factor of a given plant n, and it is given by relation ln equals to 1 by 1 minus dou pl by dou p. So we can write this as approximation for penalty factor as 1 plus dou pl by dou p. So this is the condition for penalty factor analysis. Now we have some simple problems based on penalty factor that will give you better understanding about this analysis. That is, here the problem comes like this. The first one, fuel inputs per hour of plants 1 and 2 are given as determine the economic operating schedule and the corresponding cost of the generation if the maximum and minimum loading on each unit is 100 megawatts and 25 megawatts. So the demand is now total 180 megawatts and transmission losses are neglected. If the load is equally shared by both the units, then determine the saving obtained by load. So the units as per equal incremental production cost is given here in terms of F1 and F2, where F1 is 0.2 P1 square plus 40 P1 plus 120 in rupees per hour. So F2 is given, second cost, incremental fuel cost F2, that is 0.25 P2 square plus 30 P2 plus 150 rupees per hour. Now, whatever the incremental production costs of both the units, they are supposed to be represented with the variables of F1 and F2 as a dF1 by dP1, dF2 by dP2. Now dF1 by dP1 is 0.4 P1 plus 40 rupees per megawatt, and dF2 by dP2 is 0.5 P2 plus 30 rupees per megawatt. Now if you make this for economic operation of the units, then it becomes dF1 by dP1 equals to dF2 by dP2. This can be written as, what is the value of dF1 by dP1? 0.4 P1 plus 40 rupees per megawatt. Now this value we need to write here, that is 0.4 P1 plus 40, which is equals to 0.5 P2 plus 30. Now equate these two combinations, P1 plus P2, that is equals to the 180 case. Now solutions of these equations may be written as P1, P2. So P1 equals to 88.89 megawatts, P2 is 91.11 megawatts. Now cost of generation can be written as summation of these two incremental fuel costs, that is F1 and F2. So summation now can be written as F1 plus F2. So F1 plus F2 is with F1 as 0.2 P1 square plus 40 P1 plus 120. This is 5255.88 rupees per hour. This we may obtain. Why? Because if you substitute the coefficient of P1 here with a value of 88.89, so 0.2 into 88.89 whole square plus 40 into 88.89. So plus 120. This gives a value of 5255.88 rupees per hour. Similarly, for F2 case, 0.25 P2 square plus 30 P2 plus 150. Here instead of P2 substitute 91.11 megawatts. Then this becomes 91.11, 0.25, 91.11 whole square plus 30 to 91.11 plus 1. So which is giving a value about 4958.55 rupees per hour. Now to obtain total cost, you need to add these two combinations. That means 5255.88 plus 4958.55. To add these two summations, finally you obtain the total cost as 10,214.43 per hour. Now if the load on each unit is 90 megawatts, the cost of generation will be F1 equals to 5,340 per hour, and F2 is 4,875 per hour. Now the total cost is 10,215 per hour. Now the saving will be about 0.57 rupees per hour. Now coming to second problem. The fuel cost of two units are given here as C1, C2. So C1 is with the function of Pg1, that is 1 plus 25 Pg1 plus 0.2 rupees per hour in 21 GP, and C2 is C2 of Pg2 1.5 plus 35 Pg2 plus 0.2 rupees per hour 22 GP. So if the total load demand on the generators are 200 megawatts, find the economic load scheduling of the two units. So the condition for economic load scheduling when neglecting the transmission losses are dCi by dPgi equals to lambda. So this is the condition for I equals to 1, 2, so on up to n. So that is dc1 by dpg1 equals to dc2 by dpg2 equals to dcn by dpgn. This may extend it up to lambda case. So C1 is about 1 plus 25 Pg1 plus 0.12 Pg1 square. So dc1 by dpg1 gives you 25 plus 0.4 Pg1 rupees per megawatt hour. Similarly, C2 is 1.5 plus 35 Pg2 plus 0.12 Pg2 square. So this dc2 by dpg2 is 35 plus 0.4 Pg2. So for economical load dispatch, dc1 by dpg1 is equals to dc2 by dpg2, which is equals to lambda. Now 25 plus 0.4 pg1 is equals to 35 plus 0.4 pg2, or we may write 0.4 pg1 minus 0.4 pg2 as 10 megawatts. And this combination of pg1 plus pg2 gives a value about 200 megawatts. So by solving these equations, then multiplying both sides by 0.4, we will get the simplified expression as 0.4 pg1 plus 0.4 pg2 is equals to 8. So by adding these equations, 0.4 plus 0.4, that is about 0.8 pg1, that is about 90. So Pg1 equals to 90 by 0.8, that gives 112.5 megawatts. Now substituting the value of Pg1 that we obtained about 112.5 megawatts, then 1125 plus Pg2 equals to 200. Then bring it to this side, that is 200 minus 112.5, which is about 87.5 megawatts. This is Pg2. So 3 power plants, next case, 3 power plants of total capacity about 500 megawatts, which are scheduled for operation to supply total system load of 350 megawatts. So now find the optimum scheduling if plants have incremental cost characteristics. We already discussed about input output characteristics. With that we derived cost curves and incremental fuel cost analysis. So these will represent into the system with the load demand in power versus rupees per hour. This analysis gives the cost curve representation. So according to that, the problem is given with dc1 by dp1 is equals to 40 plus 0.25 p1. That is 30 less than or equals to p1 less than or equals to 150. dc2 by dp2 gives 50 plus 0.3 p2, and which is existing in the limits 40 less than or equals to p2 less than or equals to 125. Similarly, dc3 by dp3 gives 20 plus 0.2 p3, which is about 50 less than or equals to p3 less than or equals to 225. So these are the power ranges, the coefficient existing in between them. So with this analysis, we can solve like this. For economic load scheduling among the power plants, the necessary condition is that dci by dpgi must equals to lambda. So this we must satisfy initially. So for 3 plants, dc1 by dpg1 is equals to dc2 by dpg2, dc3 by dpg3, which is equals to lambda. Now total load will be pg1 plus pg2 plus pg3, that is about 350 megawatts. So now we add all these values of pg1, pg2, and which will be equating them 40 plus 0.25 pg1, 50 plus 0.30 pg2, 20 plus 0.20 pg2, which is equivalent to lambda case. Now dc1 by dpg1 equals to dc3 by dpg3. So if you add this one, 40 plus 0.25 pg1, which is equals to 50 plus 0.30 pg2. So with this we may change it as 0.25 pg1 minus 0.30 pg2 equals to 50 minus 40, that is equal to 10. And 40 plus 0.25 pg1 equals 20 plus 0.2 pg2. With this 0.25 pg1 minus 0.2 pg3 equals 20 minus 40, then you may get a minus 20 value here. Coming to this, if you extend this analysis, 0.25 Pg1 minus 10 equals to 0.30 Pg2. Now Pg2 is 0.25 Pg1 minus 10 by 0.3, which is equals to 0.833 Pg1 minus 33.33. So this Pg1 plus 0.833 Pg1 minus 33.33 plus Pg3 is equals to 350. So or we may write 1.833 Pg1 plus Pg3 equals to 383.3. So this will be 0.25 Pg1 minus 0.2 Pg3, which is equals to minus 20. Now equating these coefficient and writing for that, 0.616 Pg1 is equals to 56.66. Or we may write Pg1 equals to 91.98 megawatts. Substituting the value of Pg1, then it becomes 1.833 into 91.98 plus Pg3 equals to 383.23. Or Pg3 is equals to 214.73 megawatts. Now substituting the values of Pg1 and Pg2, 91.98 plus Pg2 plus 214.73 is equivalent to 350. Or with this, by adding these two, 91 and 214, and with this 350, add these two and subtract into 350. So 350 minus of this one, how much? 91.98 plus 214.7. So this summation will be subtracted from 350. Finally, you can obtain Pg2 is 43.29 megawatts. So for economic scheduling of the load, the generation of 3 plants must be Pg1 is 91.98 megawatts, that we already have. Pg2 we derived here 43.29 megawatts. Pg3 is 214.73 megawatts. So like this we can obtain the economic scheduling of the load for the generation of 3 plants, that is in terms of Pg1, Pg2 and Pg3 respectively. Next case, the IFC for 2 plants are given. dC1 by dPg1 equals to 0.075 Pg1 plus 18. dC2 by dPg2 equals to 0.08 Pg2 plus 16, that is in rupees per megawatt hour. Now the last coefficients are given in terms of B11 as 0.0015 rupees per megawatt. B12 is equals to B21 is equals to minus 0.004 per megawatts, and B22 is 0.0032 per megawatt for lambda equals to 25 rupees per megawatt. Find the real power generations, the total load demand and the transmission power loss. So here we need to calculate the real power generations, P, total load demand and transmission power loss. These are the coefficient we need to determine for this given problem. So here Pg1 plus Pg2 is equal to total load demand plus load power, that is as in terms of transmission loss as PL. We know that from B coefficient, summation P equals to 1 to N, Q equals to 1 to N, Pg1, BPQ, PGQ. So as a sum product for number of plants N equals to 2, we know that transmission loss coefficient PL, summation P equals to 1 to 2, Q equals to 1 to 2, then PGP, BPQ, PGQ. So by utilizing these conditions, Pg1, B11, Pg1 plus Pg1, B12, Pg2, Pg2, B21, Pg1 plus Pg2, B22, Pg2. So summing all these B coefficients and substituting for this, what is Pg1, B11? Pg1, B11 we have already, and substitute that, and this Pg1 may goes to square term. This B11 value is 0.0015. Again here Pg1, Pg2, that product we written here, and here it is about 2 into minus 0.004. Here Pg2, B21, G1, 0.0032 Pg2 square. So if you subtract this, 0.0015 Pg1 square minus 0.0008 Pg1 Pg2 plus 0.0032 Pg2 square. Now the ITL of the first plant can be written as ITL 1 that is dou PL by dou PG1. That is about 2 into 0.0015 PG1 minus 0.008 PG. Now penalty factor can be determined for the first plant as plant 1 L1, that is 1 by 1 minus dou PL by dou PG1. This is the formula for penalty factor of the plant 1. So 1 by 1 minus 0.003 Pg1 minus 0.008 Pg2. Similarly, ITL of the plant 2 has dou PL by dou Pg2, which is about minus 0.008 Pg1 plus 0.0064 Pg2. Now penalty factor of the second plant as L2 is 1 by 1 minus dou PL by dou Pg2, which is equals to 1 by 1 minus of minus 0.008 Pg1 plus 0.0064 Pg. Now condition for optimum operation can be expressed as dou C1 by dou Pg1 into penalty factor 1 L1 is equals to dou C2 by dou Pg2 into L2 equals to lambda. So dou C1 by dou Pg1 L1 is equating to lambda first, then this dou C1 by dou Pg1 L1 is like 0.075 Pg1 plus 18 into 1 by 1 minus 0.003 Pg1 minus 0.008 Pg2, which is equal to 20. Now making this condition here and equating to this with the product of this value, then it will be cross multiplied. 25 into 1 minus 0.003 Pg1 minus 0.008 Pg2. Or we may write it as 0.15 Pg1 minus 0.002 Pg2, which is about 7. And we may write dou C2 by dou Pg2 L2 equals to lambda. And this we completed dou C1 by dou Pg1 L1 equals to lambda case. The resultant is with this one. Similarly, the second condition we need to solve dou C2 by dou Pg2 into penalty factor 2 L2 is equals to lambda. So 0.08 Pg2 plus 16 into 1 by 1 minus of minus 0.008 Pg1 plus 0.0064 Pg2, which is equals to 25. So this you equate, then 0.08 Pg2 plus 16 equals to 25 into 1 minus of minus 0.0008 Pg1 plus 0.0064 Pg2. So these are the variables we obtain when you solve for the second penalty factor with the Lagrange's coefficient lambda. Then the resultant will be 0.02 Pg1 minus 0.24 Pg2, which is equals to minus 9. Solving for these equations, and you may obtain Pg1 as 52.24 megawatts. Now substituting the Pg1 value in the respective equation, then 0.5 into 52.247 minus 0.02 Pg2 gives 7. So therefore Pg2 is 41.852 megawatts. Now the transmission loss coefficient can be represented as PL. That is PL equals to 0.0015 into 52.247 whole square minus 0.008 into 52.247 into 41.852 plus 0.0032 into 41.852 whole square. So this value is 7.95 megawatts. Now total load E can be represented as PD, that is Pg1 plus Pg2 minus PL. So Pg1 is 52, Pg2 is 41. Subtracting with this, you may get 86.14 megawatts. Next one is on a system containing 2 generating units, the incremental cost is in rupees per megawatt hour with the Pg1, Pg2 values. DC1 by dPg1 is 0.08 Pg1 plus 8. DC2 by dPg2 is 0.012 Pg2 plus 9. The system is operating on economic dispatch with Pg1 equals to Pg2 equals to 500 megawatts and dou PL by dou Pg2 equals to 0.2. Find the penalty factor of the first plant. So here we need to calculate penalty factor for the first plant. So given that the system operates on economic dispatch with Pg1 equals to Pg2 equals to 500 megawatts. So the condition for this optimal operation when considering the transmission loss is dc1 by dpg1 into penalty factor L1 equals to dc2 by dpg2 penalty factor L2 is equals to lambda. That means first one and second one both are equivalent to lambda case. So, and also it is given that ITL of the plant 2 as dou PL by dou PG2 equals to 0.2. Now the penalty factor for the second plant, that is plant 2 as L2, that is 1 by 1 minus dou PL by dou PG2. So which is 1 by 1 minus, we know that ITL2 is this one, that is 0.2, that is 1 by 1 by 0.8, that is 1.25. So for optimal condition, dc1 by dpg1 into L1 equals to dc2 by dpg2 into L2. So when you equate to this, then 0.008 pg1 plus 80 into first penalty factor L1 is equals to 0.012 pg2 plus 9 into L2. So this may be 0.008 into 500 plus 80 into L1 equals to 0.012 into 500 plus 9 into 1.25. So when you equate this, 12 L1 equals to 18.75. L1 equals to 18.75 by 12. So when you cancel this, then you may obtain with the first L1, that is first penalty factor, as 1.5625. This is the penalty factor of the first plant. Next problem is a two-bus system is shown here. This is the two-bus system. This is bus 1, this is bus 2. So if a load of 125 megawatts is transmitted from the plant 1 to the load, a loss of 15.625 megawatts is happened. Determine the generation schedule and the load demand if the cost of the received power is 24 rupees per megawatt. Solve the problem using the coordination equation and the penalty factor method approach. The incremental production costs of the plants are. So that is df1 by dp1, df2 by dp2 is equals to 0.025 p1 plus 15. And df2 by dp2 is 0.05 p2 plus 20. So this is the two bus system with bus 1 as a P1, bus 2 as P2. These are connected by one load. Since the load is at bus 2 alone, therefore losses in the line will not be affected by the generator of the plant. Why? Because load is happened here. So now the coefficients can be represented with the transmission loss coefficient PL, that is B11 P1 square as B12, which is equals to B21 equals to 0 and B22 as also 0. Now substitute these conditions with this 15.625 is equals to B11 into 125 square. So simplify for this, then you may obtain 0.001. Now coordination equation becomes df1 by dp1 plus lambda dou pl by dou p1, which is equals to lambda, where PL is equals to 0.001 P1 square or dou PL by dP1 is equals to 0.002 P1. So substituting in the coordination equation for plant 1, we will get 0.025 P1 plus 15 plus lambda 0.002 P1 as lambda. So for this 0.025 P1 plus 0.048 P1 plus 15 is given with 20. Or we may write this condition by simplifying P1, they both will be added. Then 0.073 P1 equals to 9. Now P1 is 123.28 megawatts. And from the coordination equation of the plant 2, we may write 0.05 P2 plus 20 equals to 24 or P2 equals to 80 megawatts. Now the transmission loss quotient PL is 0.001 into 123.28 whole square. So making this and producing this value gives 15.19 megawatts. Now the load is PD, that is 123.28 plus 80 minus 15.19, which gives a total load, that is PD is about 188.1 megawatts. So the solution using the penalty factor is as follows here. So the penalty factor for plant 1 is 1 by 1 minus of dou PL by dou P1 equals to 1 by 1 minus of 0.02 P1. So here dF1 by dP1 into 1 by 1 minus 0.002 P1 gives 24. And if you simplifying this condition, 0.025 P1 plus 15 by 1 minus 0.002 P1 is equals to 24. So that gives a value of P1 as 123.28 megawatts. So similarly, dPL by dP2 is 0. Therefore, L2 is unity. The incremental cost of the received power is equals to the incremental cost of the production. That means 0.05 P2 plus 20 equals to 24. With this, if you subtract this 20 with this 24 and simplify for that, you may get the value of P2 as 80 megawatts. This value will gives you the penalty factor 2. Now penalty factor 1 with the value is 123.28 megawatts. Penalty factor with value 2 is about 80 megawatts. Like that we will obtain P1, P2 values. If you add these summation, then you may equivalent to 120 plus 80 means 203.28 megawatts. This is the total power incurred you may obtain during this solving procedure. So with this we can conclude for the penalty factor analysis, and these are some of the references that I have considered to derive these penalty factor conditions and simple problematic analysis. So thank you. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.